Hello friends, I welcome you to my YouTube channel Bank PM. In today's video, we are going to see very important case. Here, this vane or this unsymmetrical blade is representing almost similar case to a turbine blade. So let's see this. This is a unsymmetrical plate, or also called a vane. This water jet is striking this blade in a tangential direction, and the VR1 is relative velocity with which this jet is striking this blade. Why VR1? Because this jet is striking in with the absolute velocity V1, but this blade is also moving with a velocity U. So effective or relative velocity along with which this jet is striking this blade is VR1. So VR1 is relative velocity at inlet. Similarly, VR2 is relative velocity at outlet. These two triangles are also called velocity triangles at inlet and outlet. So let's see the various parameters. This is alpha. Alpha is the angle with which this jet is striking this blade with absolute velocity. Theta is the angle with which this relative velocity this jet is striking with relative velocity of VR1 to this blade. So this alpha is also called the guide blade angle. This is called guide blade angle, and this theta is called vane angle at inlet, and similarly beta and phi are at outlet. This is VW1. VW1 is the horizontal component of this V1, absolute velocity in horizontal direction, and F1 is in vertical component. So you can see that U1 is the velocity of blade at inlet, and U2 is velocity of blade at outlet. Now if you see, the force is equal to rate of change of momentum m, which is equal to m1 minus m2 divided by time. Here momentum is mass into velocity, so m1 v1 minus m2 v2 divided by time. Here m1 and m2 are same because mass flow rate through this mass coming out of this jet is constant, so mass flow rate will be constant. So m1 and m2 will be same, so m1 and m2 will be same, so it will become m v1 minus v2 divided by time. M by t is mass flow rate. Mass flow rate will be density into volume per unit time. So density is rho, and volume is area into velocity per unit time. So area into VR1, because VR1 is relative velocity at inlet. So this is volume of jet which is striking this blade, and V1 minus V2 is the velocities. Now if we have to find out the force exerted in horizontal direction, then we can write it like Fx in horizontal direction is Fx is equal to rho a VR1 in bracket V1x minus V2x is equal to rho a VR1. What is V1x? Velocity in x direction at inlet. What is velocity in x direction at inlet? This is equal to this CD. What is the value of CD? It is equal to VW1. This VW1 minus this U1. So it will be VW1 minus U1 minus what is the velocity V2x at outlet? It is equal to this GH, which will be equal to U2 plus VW2. U2 plus VW2. Now you can see that this velocity is in opposite direction, because after coming out of this blade. This is moving in this direction. So this component is, this velocity is in opposite direction to this inlet direction. So this will be minus, because these two are in opposite directions. So it will become rho a vr1 in bracket vw1 minus u1 minus minus will become plus, plus u2 plus vw2. Now you know that u1 and u2 are the velocity of blade at inlet and outlet, which is equal to u, because velocity of blade is constant. So u1 and u2 will become 0. No, u1 and u2 will become equal to u. So u minus u will become 0. So rho a vr1 in bracket vw1 plus vw2. This is the force exerted in horizontal direction. Now you have seen that the force exerted in horizontal direction on this blade is rho a vr1 vw1 plus vw2. But suppose that this angle beta is more than 90 degree. So this angle at which this vr2 is coming will be in somewhere in this direction, and vw2 will be in this direction, and triangle will be like this. So here vw2 will become in same direction. So force can become rho a vr1 vw1 minus vw2. That's why we can write it as, so we can write it as rho a vr1 in bracket vw1 plus or minus vw2, because it can be plus or minus. Now this is the force in horizontal direction exerted by this this jet on this blade or vane. So what will be the work done? Work done is equal to force into displacement fx into d. So work done per unit time is equal to fx into velocity, in direction of force. So work done per unit time, wt is equal to rho a vr1 vw1 plus minus vw2 into what is the velocity of this when in direction of force is equal to u. So it will become work done per unit time is equal to rho a vr1 into u vw1 plus minus vw2. So this is the work done on this vane by this jet. What will be the efficiency of this jet? See, this is the output work done, output energy, and what is the energy at inlet is equal to half mv square, because you can see that initially jet has a kinetic energy, because the jet water was moving with the velocity of v1, absolute velocity of v1. So kinetic energy at inlet will be half mv square, which is equal to half rho a v1 square into, yes, mass is rho a v1, sorry, mass is rho a v1 into v1 square is the velocity square. So it will become half rho a v1 to the cube. So this is inlet and this is outlet. This is input work energy and this is output energy. So efficiency will be work output upon work input, or energy output upon energy input, which will be equal to rho a vr1 u vw1 plus minus vw2 divided by half rho a v1 cube. So this rho will cancel this rho, a will cancel a, so this will become vr1 into U in bracket VW1 plus minus VW2 divided by half V1Q. So this is efficiency of this jet. Now you can see that if this jet relative velocity is making at an angle of 90 degree from here, from horizontal, or it is exiting in vertical direction, then VW2 component can be 0. So we can get work done, or force also. This can be 0 if this angle is 90 degree. So it can become rho A VR1 into VW1. I hope you understood how to calculate the work done, force and efficiency of the jet in this problem. If you like this video, then please subscribe my channel. Thanks for watching.